Okay, beyond the standard one, homework 4 is out, both about covers neural networks and Bayesian learning, stuff that we're going to talk about today. We have extended, or I'm extending now, the due date so that you have actually one more weekend. And hopefully that means that you can take Thanksgiving off and take it a little bit slower. So we changed it to December 7, which is Monday, 2 weeks from today, I think. Okay, so also no lecture on Wednesday. Wednesday is still a teaching day at Penn, but it's running under Friday schedule. So we're going to be off for a week. We will have a recitation this week, so please go. We're going to cover mostly neural network things that are related to the problem set, and beginning to cover a little bit of probability theory if you have questions. Comment on the projects. So hopefully we are running well. All of you are writing a proposal or already submitted a proposal. We assigned a TA to each one of the teams so that you have someone to ask questions and help guiding you if needed. You should all have received email from your guiding TA. If not, let me and or Ben know. And we also have finalized we have a date for a final, a day for the project submission. Look at the class website, it's all spelled out there. Questions? What about homework 5? There will be homework 5. It will be around the last week of the semester. Okay, so if I forget to say at the end, happy Thanksgiving. Hopefully you will have a chance to take a little bit of time off. I definitely am looking forward to it, so I'm sure you too. And let's start. Okay, project, I don't think there's anything new here. Homework 5, if I remember correctly, will not involve any coding. So we expect it to be shorter. Okay. So any questions before we start? Okay, so where are we? So what we've done so far in the class is what I call here error-driven, or you'll see in the literature as discriminative learning. So basically, we assume that there is some distribution over X cross Y. X are instance space, Y set of labels. And really, we think about the data generation process as governed by some distribution D of X, and the labeling process governed by D of Y given X. But we don't know anything about D. And in fact, we don't need to know anything about D. Because if D is known, really there's no learning, right? So we can just predict Y as the argmax over all possible Ys of D of Y given X. Or if we're looking for a hypothesis, same thing, we're going to find the hypothesis that minimizes the error that we're making. And if the distribution is known, we can just do that. So the interesting case for learning is that when we don't know D, and this is actually the protocol that we've discussed, or the set of protocols we've discussed throughout the semester. So today we are going to think about a slightly different protocol that is called Bayesian learning, or sometimes generative learning. And we'll see what are the differences first between two. So just to illustrate the difference, I'm going to use again this running example of text correction. Given a sentence, I saw the girl eat the park, I want to be able to correct it to the I saw the girl in the park. So in the discriminative paradigm, or the direct learning, we really model the problem of text correction as a problem of learning from examples. And our goal is to learn how to make predictions. So we're looking at many examples, discover some regularities in the data, and this allows us to construct a prediction policy. So a prediction policy, some kind of a function, a predictor, could be something like a rule, right? So it's the it-in rule. If you see the word the before the target word, change this target word to in. Of course, the rule can be more complicated, could be a linear threshold function, could be a neural network, but basically it's a rule that takes some property of the input or multiple properties of the input, compute the functions on it, and makes a prediction. Now, of course, we're making assumptions for this to work, and the assumptions are really coming in the form of the hypothesis class. What types of functions are we going to allow our learner to use? And in this case, I used a very simple set of functions, just an if-then rule. In general, you can use a more expressive class of function. As I said, linear threshold function, decision trees, neural networks. But the bottom line is that really what we're doing by approximating this hypothesis that maps from X to Y is we are estimating the probability of Y, the labels given X. And you know, we talked a lot about this. We discussed sort of in details the learning protocol, how to find these H's by minimizing some empirical error plus a regularization parameter. We talked about various losses that we can minimize. And we also talked about the fact that we have guarantees. And basically the guarantee is that if we find an algorithm that minimizes the loss on the observed data, then learning theory guarantees that things are going to be okay. Of course, as a function of the size of the hypothesis space we're dealing with. So that's what we've done. The next paradigm that we're going to start playing with today, which I call here a generative paradigm, models the problem of text correction as that of generating correct sentences. And the goal is to really learn a model of the language. And once we know what is more probable than not, we use this to predict. So we're going to learn a probability distribution over all sentences. Of course, this will force us to make some assumptions on the type of distribution or the family of distribution that could govern the generation of these sentences. We cannot start without any assumption with working with the space of all possible distributions. But once we make this set of assumptions, we're going to use it to estimate which sentence is more likely under our family of distribution. Is it I saw the girl eat the park, or I saw the girl in the park? Of course, our decision policy depends on these assumptions. And at the end, we're going to have this probability distribution. We're going to know how to compute P of X, Y. And this will allow us to choose the most probable sentence, which indirectly, of course, will tell us whether we need to replace something in the old sentence and convert it to the new sentence. So the model is called generative because we're going to make assumptions on how the data X is generated given the label. And we'll see a lot of examples for this today. And of course, it comes with guarantees. If we assume the right family of probability distribution, we're going to have guarantees that what we're going to do is the right thing, because observing data will allow us to choose a specific member in this set of probability distributions. And this is the right distribution. Once we have the right distribution, as I commented earlier, we can just make a decision. We are done with the learning. Okay, so that's actually what we're going to talk about today. We're going to give a few examples that will clarify things. I just want to make a comment before we start that sometimes confuses people. So really, when we think about probabilistic learning, there are two different notions. One of them is just learning a probabilistic concept. And in many respects, everything that we've done so far when we learn hypotheses, you can view them as learning a probabilistic concept. We really learned a function, and quite often we learn a function that maps x into the interval x1, or we normalized it into the interval x1. We can interpret this h of x as a probability distribution. Sometimes it's a correct interpretation, sometimes it's not really a correct interpretation, but one can maybe tune h so that the output can be interpreted as a probability distribution. But the important thing is that when we do it this way, the learning theory that we developed earlier this semester applies. We did develop it for Boolean functions that maps things into plus or minus 1 or 0, 1. But actually, with a little bit of an extension, everything that we said on Boolean function would apply also to functions that range between 0 and 1. On the other hand, when we talk about Bayesian learning, the difference is how do we select the hypothesis? Here we're going to use a probabilistic criterion in selecting the hypothesis. The hypothesis can be whatever you want, can be a Boolean function, can be deterministic. So it's really not the hypothesis that matters here, it's the process that leads us to select a hypothesis. At the end, we're going to fold these two together, and we'll see that in practice, really what's happening in Bayesian learning in many respects can be viewed also from the perspective of good old learning theory that you all know already. Okay, so now we're ready to start. Now, one thing that I'm not going to do here is I'm not going to remind you of basic probability theory. I'm assuming that you've all covered it. We gave you a couple of quiz questions about it with the goal of bringing this to the top of your head so you know how to play with it. In fact, you know the key tool that I'm going to introduce shortly, which is Bayes' rule. I'm just going to remind you of that. Oh, that's not what I wanted. So there are a lot of slides that I'm skipping now that could provide you with some introduction or summary of what you already know in basic probability. I'm skipping them and just going back to a summary that, again, I expect you all know about it. We know about the product rule. So when we write P of AB, which is another way of saying P of the events A and B happening, we know that we can write it this way, P of A given B times P of B, but also P of B given A times P of A. You understand the notion of independence. We're going to go back to it hopefully at the end today. It's a really important notion that we're going to count on. You know the notion of Bayes' rule. I'm going to come back to it in a second, but I know that if you solve the quiz questions, you're already familiar with this. And you also want to know the notion of total probability, the fact that you can represent a probability of an event B as a sum of the probability of B and AI, where AI are mutually exclusive events, as written here. So I'm assuming that all this is good. Just to test yourself, here is a problem that I'm assuming many of you are familiar with, known as the Monty Hall problem. Here is how it goes. You know, suppose you're in a game show. You're given the choice of 3 doors. You're told that behind one of them, there's a car. Behind the 2 others, there's a goat. Under the assumption that you prefer to choose the car over the goat, your goal is to guess where would the car be. So you pick a door, say you pick door number 1, and the host, who knows, of course, what's behind the doors, opens another door, say doors number 3, and shows you there's a goat here. Now notice that this can always be done, right? Whatever is behind the door that you chose, number 1, they can always choose one that has a goat behind it because there are 2 goats. So they didn't do anything sophisticated. And then the host asks you, do you want to switch to door number 2? And my question is it to your advantage to switch or not? Guesses? It's okay if you knew this problem already. Are you going to change your choice of door number 1 or not? Okay. Most of you, all of you here say switch. And that's right. But the exercise that I'd like you to think about is try to develop a rigorous argument using basic probability theory, basically use Bayes' rule, as a way to justify why switch is the right choice. So again, take this as a homework question, use Bayes' rule, and convince yourself that switching is the right thing. And ask this question over Thanksgiving meal if your family doesn't know this. And let's move on. So Bayes' rule is going to be the key tool we're going to use. A very simple rule that you kind of already know, and really is the most important most important formula in probabilistic machine learning. Basically, it says that P of A given B can be written as P of B given A times P of A divided by P of B. And the proof is also trivial. We know the product rule is that P of A and B can be written as P of A given B times B of B. P of B given A, which is the same thing, can also be written as P of B given A times B of A. And these are just equal. And that's why you can write P of A given B this way. And just a notation convenience, we're never going to use anymore P of A and B, which says both events A and B happen, but rather we're going to call it P of A comma B. That's the common way to use it. So now that you've seen Bayes' rule again and reminded of it, I'm going to change notation to the notation being used in machine learning. And in machine learning, rather than just calling it events A and B, we're going to call it evidence and hypothesis. So basically what we're going to say that the probability of the hypothesis given the evidence is the probability of the evidence given the hypothesis times the probability of the hypothesis divided by the probability of evidence. Just think A and B from the previous slide. It's the same thing. But it has a very specific meaning, and let's summarize what do we mean when we talk about it. So really, what is Bayesian learning? So our goal is to find the best hypothesis from some space of hypothesis, given data, given the evidence. And by best here, we're going to mean the most probable hypothesis. In order to do this, of course, we need to assume a hypothesis space H, and moreover, we have to assume a probability distribution over this space of H's. And of course, we need to know something about the relation between the data that we observe and the hypothesis. Right? Think about a coin toss, right? So the probability that you get a head or a tail is related to the observation. So if I tell you the coin is a fair coin, you know something about the probability of observing head or tail. You know it's about the same. If I tell you that this is a biased coin and the probability of head is 0.8, you know something about the expected observations that you're going to see. So that's what I mean here by the relation between the data observed and the hypothesis. And so these are the basics. Of course, as we'll see even later today, you can be Bayesian about other things, not necessarily a hypothesis. We can be Bayesian about the parameters of the model, which is another way of saying choosing thinking about the probability distribution over a set of functions. Okay, so let's dive down to the basics of Bayesian learning. So we have these 4 components that we care about. By P of H, we denote the prior probability of the hypothesis H. So H is a member of capital H, and this really reflects the background knowledge that we have. Before we've seen any data, what is the prior probability we assign to each member of the hypothesis space? If we have no background knowledge, then we're going to assume uniform distribution. So P of H is going to be the same for all H's. P of D is the probability that this sample D of the data is observed. Again, in this case, we have no knowledge of the hypothesis. We just look at the data. P of D given H is the probability of observing a given sample of data D, given that the hypothesis is H. And what we care about is P of H given D, the decision made by the learning process. What is the probability of a given hypothesis given the observation D? And we call this the posterior probability of H, the probability that H is the target given that D has been observed. So now that we take these components and we can place it inside Bayes' theorem, P of H given D, which is what we care about, the posterior probability, is P of D given H times P of H divided by P of D. And if you just think about it from first principle, it should make sense. So the posterior P of H given D goes up with P of H, right? So if the hypothesis is more probable without any data, it's gonna increase the posterior of it. It also goes up with P of D given H, right? So if the data that you observe is probable, then it increases the probability of the hypothesis that you're dealing with. And of course, P of H given D decreases with P of D, because if the data is very likely anyhow, it reduces the chance that it's because of H. Okay, so what is the learning scenario given that we have this principle? So this is Bayes' rule again. The game is as follows. We are considering a set of candidate hypotheses, H. And within this capital H, we try to find the most probable one, given the observed data. And we're going to use this rule in order to find the most probable H. We're going to call this a maximum a posteriori hypothesis for MAP. And basically, we're going to use Bayes rule to compute it. So HMAP is going to be the argmax of PH given D over all H's. Plugging in Bayes rule, it's the argmax over all H's of this ratio, P of D given H, P of H divided by P of D. And notice that I don't care when I compute HMAP, I don't care about P of D because it's not part of my argmax. So I can get rid of the denominator and just say that it's the argmax of the product, P of D given H, P of H. Okay, so again, looking at the learning scenarios, we derive this rule for what is the maximum a posteriori hypothesis that we have. Now, what happens if we don't have background knowledge? We don't have priors. We assume that all the hypotheses are equally likely to appear, which is written this way: P of HI is equal to P of HJ for all HI HJ. In this case, I can eliminate this part from the argmax also, because all the P of HI are the same. And what I'm going to get is just argmax over P of D given H. And this is going to be a special case of the maximum a posteriori hypothesis, which we're going to call the maximum likelihood hypothesis. And essentially, what that means is the chosen hypothesis is the one that best explains the data, right? So you choose the hypothesis such that the probability of the observed data given it is maximal, which hopefully makes a lot of sense. Okay, so let's start with a given example. And we're going to start with a coin toss example. So this is Bayes rule. And just to remind ourselves as we work this out, and I'm going to assume that I'm tossing a coin and I know that there are two possible hypotheses. Either it's a fair coin, 50-50, or it's a biased coin, 60% in favor of head, right? So my learning problem then is choose the right hypothesis, whether it's the fair coin or it's the 60% head coin. So my hypothesis space here only has two hypotheses, right? H1, which is P of H is a half, and H2, P of H is 0.6. That's the learning problem. What do I do? If I have a learning problem, the first thing I want to do is get some data. Okay, before that, I'm going to make an assumption on my hypothesis space. I have priors. I'm assuming that H1 is more likely than H2. Specifically, I'm going to assume that P of H1, the prior distribution of H1 is 0.75. The prior distribution of H2 is 0.25, right? So I only have two hypotheses. The sum of the priors has to sum to 1. Now I can look at data. So in my first experiment, I tossed the coin and I got H, head. Now let's look at the other components of Bayesian learning. So I already have a prior. This was component 1. Second component, probability of D given H, the probability of the data given H. So let's see. I know that I got H. This is my data. I tossed the coin and I got head. So what is the probability of the data given H1? It's 0.5. What is the probability of this observation given H2? It's 0.6. What is the probability of the data? So this is without any commitment to a hypothesis, what is the probability of observing ahead? So the probability of observing ahead is the probability of observing ahead given that it's H1 times probability of H1 plus the probability of observing ahead given that it's H2 times the probability of H2. So this is what I call the total probability formula. Hopefully you're all comfortable with this. And therefore, I can compute it now. So this is 0.5 times the prior 0.75 plus 0.6 times the prior 0.25. I get that the probability of observing ahead is a little bit more than a half, actually, 0.525. Now that I have these three components, I can compute the posterior. What is the probability of H given D? So for H1, just plugging in into Bayes' rule, P of D given H1, P of H1 divided by P of D, I get that the probability of H1 is 0.714. P of H2 is 0.286. So clearly my posterior is now, it's more likely that it's H1. Now remember that I started with this very, very tilted prior. And given that I got 8 ahead, in fact, I'm less biased now than I was before, right? And it makes sense because H2 has a higher probability of seeing ahead than H1. So I'm moving a little bit more toward H2. So this result should make sense. Question so far? Everyone is clear about what we've done, about the protocol of Bayesian learning? Okay, so now all we did is we tossed one coin. This was our data point. What you can do as an exercise is do it many times. So toss the coin 100 times and repeat the math. So again, this is a summary of what we've done, but and just a comment here. If we were to use the maximum likelihood approach, that is, P of H1 would be equal to 0.5, would be equal to P of H2, our conclusion would have been different, right? So at this point, we still think that the coin is more likely to be fair because we started with such tilted priors. If we were thinking that these are equal priors, after observing ahead, we would probably be more biased toward this hypothesis H2. You can try to plug it in here and make sure that you agree with that. Okay, but the next step that I'd like you to do is actually try 100 coin tosses. Let's assume that when you tossed it 100 times, you got 70 heads. You can just go ahead and compute it. It's computed in the next slide. But hopefully, intuitively, you all agree that at this point, you would be 100 coin tosses is going to be sufficient to convince you that H2, my second hypothesis, is more likely than H1. Okay, so you will believe that the coin is biased, and I'm just giving the math here in this example. I'm not going to go over it, but you should go over it, convince yourself that you agree with it and you know how to do this. Okay, so this was a simple problem of thinking about a very simple hypothesis space, two hypotheses. But in real life, I'm not going to tell you ahead of time, look at this coin, there are only two options. You will look at the coin and you'll say, well, there's infinitely many options for the bias of the coin. Any real number, P, between 0 and 1, could be the hypothesis, could be the bias of the coin, which is our hypothesis here. So what would you do if you have infinitely many hypotheses to choose from? We will still follow the maximum likelihood principle. And this is my first question to you. Assume that you toss a P, 1 minus P coin, M times, and you get K heads, M minus K tails. What is your estimate for P? So start guessing. My next question is going to be why. So think also about the why. So I'm going to give you a minute to think about it. I'm going to stop my video for a second while you're thinking about it. Okay, so not everyone has thought about it yet. So anyhow, let's see what you guys are thinking. Okay, several answers, but I think the largest one here is K over M. So K heads, M tails. Most of you believe that it's K over M, which is right. If you were not sure that it's K over M, think again and convince yourself that it's K over M. And my next question is why? Or more than why, I want to know what drives this estimate. So next question is why? What is the rationale for this estimation? How can you justify it? Because I can tell you, you know what, I think it's a quarter. And you should be able to argue that your answer, this K over M, makes more sense than my answer, a quarter. How would you justify that your K over M is better than my suggestion? It's a quarter. Okay, so let's start looking at the answers here. Okay, so we don't really need to say not sure because I'm looking for those that have an idea or are willing to commit to something. Most of you wrote K over M. And why did you write K over M? It's the MLE. Okay, maximum likelihood estimate. So that's the only answer so far that makes sense. Here is another one that thinks about it from the maximum likelihood estimation. So that's the only acceptable answer here, right? So basically, it's true that the answer is number of successes divided by time fleet, but why is that the answer? And really, the only issue is that if I tell you, I think it's a quarter, you should say, no, my answer is more probable. K over M is more probable than a quarter because the probability of observing K tosses, K heads, when you toss M times is higher if the bias of the cone was K over M than if it's a quarter, right? So you can take these two cases of, I think that the bias is a quarter, you think the bias is K over M, which one of them justifies the observation that I'm making better? Okay, and I think many of you thought about it this way, and let's just quantify this. So some of you just gives me a procedure, which is right. I mean, that's what you're doing, but why you're doing? But some of you actually justified as a maximum likelihood over the binomial distribution. So let's just do this. So here's the question that I ask, and let's try to prove that indeed K over M is the right answer. And the only principle we have here is this maximum likelihood estimate. We want to show that the best, the most probable bias must be this K over M. So here is how we're going to do it. We're going to do it this way. So if P is the probability of head, the probability of the data we observe, which is K heads in M tosses, is P to the K, 1 minus P to the M minus K, right? These are independent, M independent coin tosses, so that's why we get this product. It's easier to deal with these things when we take the log. So I'm going to take the log probability. So L of P, taking the log of this expression, is K log P plus M minus K log 1 minus P. And again, we've already gone through this many times this semester. It doesn't matter which base you're taking it. This is true every time. So now I can ask myself, okay, I want to maximize the value of this expression and find what value of P maximizes it. So what value of P maximizes the probability of the data I observed. So we're going to compute the derivative with respect to P and set it to 0. So this is the derivative relative to P, d log likelihood dP. It's K over P from here minus M minus K1 minus P. If this is equal to 0, solve it, and you will see that P equal K over M. So really K over M is the right solution here in a well-defined way. But we made assumptions. We assume that the model is binomial, right? We assume that if P is the probability of head, the probability of the data observed is this. You could assume a different probabilistic model and you will get a different result. And in fact, you'll do some of this in your problem set. And we're going to talk now about multiple probabilistic models because it matters. It matters what is the probabilistic model that you assume governs the generation of the data. So next, we're going to see that this actually matters. The second important comment is that in practice, you want to be able, you need to smooth. And by smoothing, I mean, notice that if the number of coin tosses M was very small, and for example, you would get 0 heads, you don't want to say that the probability of head is 0, right? Because it could be that you just haven't seen heads yet because you tossed a small number of times. So in practice, you want to be able to smooth things away from 0. And we're going to do this every time we estimate parameters, and we're going to show at least one way of doing it in the future. So, okay, so basically, so far we've used Bayes rule, and in some sense we are done with Bayesian learning. Bayes rule is all there is. Everything is just examples of how to use Bayes rule, how to choose the set of hypotheses, and how to choose the probability distribution or the family of probability distribution that governs the generation of the data. So what I'm going to do next is I'm going to give a few more examples before we try to make this kind of practical and build models using this. So I just want to summarize a few probability distribution. Again, I'm assuming that you've seen this in your probability classes. So, but still, it's good to see this again. So we already talked about the Bernoulli distribution, which is, we have a random variable that takes 2 values, say 0 and 1, haired or tailed, such that P of X being 1 is P, P of X being 0 is 1 minus P. So this is just the probability of tossing a coin. And using this, we can also define the binomial distribution, where we have a random variable that takes n values, representing the number of successes in Bernoulli trials. So think about multiple coin tosses, and what is the probability that you get k heads? It's k choose n choose k times p to the k 1 minus p to the n minus k. And these two families of probability distribution are related in the following way. So if X is binomial with probability P and Y is Bernoulli with probability T, X is just the sum of n Ys, right? So again, think about tossing a single coin in this case, or tossing multiple coins, n coins in the second case. So these are two distributions that you've seen. And now I can actually shift this pair of distributions to the categorical case and define two other probability distributions. Let's just start with this. The first one is going to be called categorical distribution. And I'm moving from flipping a coin to tossing a dice. The random variable in this case takes values in 1 to k, with the probability of X being I, being PI, where the sum of the PIs is 1. So again, think about a dice where k is 6. If the dice is a fair die, then P of X being I is a 6. Right? And then from this, I can move, just like I move from Bernoulli to binomial, I can move to the multinomial distribution, where I'm asking what happens when I have multiple dice. So in this case, I have a random variable xi that indicates the number of times I observed I over n trials, just like before, only that now I'm tossing a dice rather than a coin. So you can think about the results as a vector x, which is x1 up to xk, that tells me how many times I got the outcome I when I did n trials. Right, so I get this x1 up to xk, where I'm using the same PIs as before, and the sum of the PIs is 1. So in this case, what is the probability distribution? The probability that I observe the values x1 up to xk in n trials with the vector p, p1 up to pk probabilities is p1 to the x1 product p2 to the x2 up to pk to the xk, where the xi's are the results of my experiments times this multinomial coefficients n factorials divided by x1 factorials product up to xk factorials. And again, think about tosses, n tosses of k dice, and think about, let's say you have 2. What is the probability that I got 3 in the first one and 6 in the second one? Okay, so I assume that you've seen this before, and I want to use it in an application. So how do we use it when we want to do learning over some generative processes? So let's think about the following application of document classification. So we are given a collection of documents. I'm assuming that my alphabet, the set of words in my language, is just A, B, and C. I only have 3 characters. So all the documents are going to have the same length, N, and the words can be either A or B or C. Very simple model that I'm kind of going to use as a way to simulate or approximate, if you want, a document classification process. Now, we are given a labeled document collection where the label could be either 0 or 1, good or bad, right? So I have a collection of documents that are labeled and come from 3-word vocabulary. And my goal is to predict, that is, eventually I'm going to be given a document and I want to predict, is it good or bad? Now, so you can imagine how you would do it in the discriminative model, right? In fact, you've done very similar problems before, and you will do, and you're doing one in your current problem set. So given a collection of documents that are labeled, learn a model to predict whether you like this document or not. Now, in the generative story, we're going to do this a little bit differently. Basically, we're going to go in a generative way. So what does it mean to go about it in the generative way? How are we going to make this a learning problem? I'm going to assume, I'm going to make an assumption on how these documents are generated, which means I need to assume a family of probability distribution that could have governed this generation process. And once I understand this process, I'm going to look at the data, estimate the parameters of this, and now I know everything. So let's do this. So what is our generative process here? I'm going to use the multinomial distribution. That's not the only option I have, but given that I just introduced it, it's a reasonable model. What is the generative process given this? First, it decides whether to generate a good document or a bad document. So it basically decides whether P of Y is going to be, whether Y is going to be 1 or 0. And it's going to decide this with this probability eta, right? So eta is the probability of generating a good document. 1 minus eta is the probability of generate a bad document. Once I decided what is the label of the document, I'm going to place words in the document. So it's going to be A or B or C. And I'm going to denote by AI, or respectively BICI, the number of times A or B or C appear in the document DI. Okay, and of course, since I said that all the documents have the same length, then I know that AI plus BI plus CI is N, the size of the ith document. But all the documents have the same length, N. Okay, so now that I decide on the process, what is the probability of observing a given document? So what is the probability that a given document DI of a given document DI, given that the label is 1? It's a good document. So here is the probability. It's alpha 1 to the AI, beta 1 to the BI, gamma 1 to the CI, times this multinomial coefficient, where the alpha, beta, and gamma are the probability of generating A or B or C in a good document. So again, think about a three-sided dice, right? So you know that you're in a good document, and now you need to generate words into the document. So you're tossing these three-sided dice. One side says A, another one says B, a third side says C. The probabilities of A, B, and C in a good document are alpha 1, beta 1, and gamma 1. And therefore, the probability of observing an N-size document with AI A's, BI B's, CI C's is this. And similarly, I have these other probabilities, alpha 0, beta 0, and gamma 0, that govern the bad documents dice, right? So the probability of observing A, B, and C, respectively, in a bad document is going to be alpha 0, beta 0, gamma 0. And of course, these three sum to 1, and these three sum to 1. Question so far? So basically, what I described here is a generative process of generating a document under these assumptions, right? The assumption that I have this equal size document, N, only 3-character vocabulary, and these probabilities. Eta is the probability of being good or bad, and the alpha, beta, and gammas, that we have two sets of these. One given good documents, another set given bad documents, governs the vocabulary placement into the document. So now notice that this is an infinite class of probabilistic models, right? Because the eta, the alphas, betas, gammas can be any real numbers that you want, modulo these constraints, right? They have to sum to 1. These three have to sum to 1, these three have to sum to 1. But still I have a very large class of documents. And now the process is, now that you assume that this is how documents are being generated, you're gonna collect documents, estimate these 7 parameters. And once you have these 7 parameters, you know exactly how a document was generated. And when you look at a document, you can count the A, B's, and C's, and you know what's the probability of it being 1 or 0. So let's just do this. So again, I want to highlight the differences from the discriminative case. The game here is different, right? So in the discriminative case, I only make an assumption on what is the model that I'm going to learn. Am I going to use a decision tree? Am I going to use a linear function? Am I going to use a neural network? And I'm going to extract features. The features could be, how many A's do I have? How many B's do I have? How many C do I have? Or there could be other features. But basically, that's the only thing I'm going to do there. And then I'm going to learn from my label data, right? This collection of labeled documents. Here, the game is different. So first, I'm going to make an assumptions on how the data is being generated. And the assumption is multinomial family of distributions with eta, alpha I, beta I, gamma I. Then I observe the documents. These observations using Bayes' rule allow me to estimate the parameters. That's my learning problem. Once I know the parameters, I predict, I can compute the probability of each document, again, using Bayes' rule and the known parameters, and I can make a prediction. So the key question is, how do we learn? And then let's just do this. Questions on the model first. It seems complicated because there's a lot of notation, but really, conceptually, it's exactly the same thing as the coin problem that we had, right? So there we had one parameter P. We made the assumption that it's a binomial distribution. Then we generated data from this binomial distribution, and we estimated the P. Now we have 7 parameters instead of the 1 parameter there, but it's exactly the same thing. We made the assumption that the probability distribution has 7 parameters. We're going to generate data and find the most likely values of these parameters. Okay, so, and the classification problem at the end is going to be given a document, determine if it's good or bad. That is, estimate P of Y given D. Right? But what is P of Y given D? It's P of D given Y, P of Y divided by P of D. Bayes' rule. So we need to know the parameters of the model in order to compute this probability. So how do we estimate the parameters? How do we solve the learning problem? So again, there's a lot of notations here, but it's really very simple. So let's just go over this. So we want to find the most likely value of the parameters, just like we did with the coin toss. Only that now the expression is going to be a little bit more complicated. We're going to write PD, which is the probability of the data. It's the product over all documents I, P of Y comma DI, which is P of D given YI, P of YI. Right? Remember that P of YI was eta or 1 minus eta. And we can compute P of D given I. So now let's see, how do we write this? So the expression that I'm writing for P of Y comma DI is product over all I. Now notice, if P of YI, if YI is 1, P of YI is eta, so it's the left component here. If YI is 0, the probability of YI is 1 minus eta. It's the right component here. Now, I don't know what is it going to be. I don't know if it's going to be 1 or 0, the value of YI. So how do I write an expression of this if I don't know what is the value of YI? So here is the trick that I'm using here. Okay, so this is just to show you that this is, I have labeled data. And I'm using the following trick. I'm taking the expression eta times the multinomial probability in the case of Y being 1. That is, I'm using the alpha 1, beta 1, gamma 1. And I'm raising it to the power of YI. What does that mean? If YI is 1, this expression is just as is. It's something to the power of 1. On the other hand, if YI is 1, 1 minus YI is 0. And therefore, this kind of disappears. It becomes equal to 1. So really, when the value of YI is 1, the probability is this. When YI is 0, this guy disappears. It becomes 1. And what I get is that the probability is this expression. So basically, this is a trick, an important trick, to write down the joint probability distribution, even though I don't know what is the outcome of the experiment. I don't know if in the ith document I got YI equal 1 or YI equal 0. Right? So this expression is a compact way of writing it without kind of knowing ahead of time what is the value of yi. It's not the only way of doing it, but it's the most useful way of doing it, as you will see in a second. So now that I know how to write down the probability, the joint probability distribution, I want to maximize it with respect to each of the parameters. So what I have to do is I have to differentiate with respect to 7 parameters, 7 times. I'm going to do it here just with respect to 1 parameter, the easiest. Before we do this, it's much easier for us to do this to compute the log. So I'm going to compute the log of PD, the log of this expression. This is one reason why this trick is useful, because it's written with powers here. So when you take the log, it's easy. What do you get when you take the log of this product? You get sum over all i's from the product. Here we get sum. Yi, this power goes to be the coefficients here, of log eta plus, from this guy, I get AI log alpha 1 plus BI log beta 1 plus CI log gamma 1 plus some constant. This guy becomes a constant, an additive constant. I don't care about it because it's going to disappear. It doesn't depend on the parameters. Plus the same thing here, 1 minus yi from here, and then log 1 minus eta. I have another constant, which is this, and these coefficients, AI times alpha 0, log alpha 0, BI log beta 0, CI log gamma 0. So I get this expression. Completely equivalent to what we've done with the coin toss with a single parameter. Now I can differentiate. And in this case, I'm differentiating relative to eta. You can see that everything disappears. And all I get is yi divided by eta from here, minus, because of this, 1 minus yi divided by 1 minus eta. If I want this to be 0 because I want to maximize this expression, and I want to find what value of eta maximizes this, then I'm going to get the eta is the sum of all yi, the sum of over i's yi over m. And hopefully, if you think a little bit about this, this should make sense to you. It's a slight extension, if you want, over the coin tosses, right? So what is the probability that eta, which is the probability that a document is good? It's the number of documents that were good in my collection divided by the number of documents, right? That's basically what I got. So hopefully this makes sense to you. Now, you can do the same thing for each one of the parameters. There is one complication here that I'm not going to deal with now. And the complication is that the parameters, the 7 parameters, are not independent. So eta is independent of all the others, but the alpha, beta, and gammas are not independent because they have to sum to 1. So you can compute 2 of them and then derive the 3rd one, or you can solve it as an optimization problem with this constraint, right? So you've already seen in your calculus class how to optimize a constraint set of parameters. I'm not going to get to it now. Questions? Oh, question is, where does M? So M is the size of my collection, how many documents I have. If it wasn't written in the previous slide, it should have been. But this is the number of examples I have. Other questions? Okay, so basically, as I said before, we actually know Bayes theory. We've done everything we need to do. Everything is now making two steps conceptually. One is choosing the hypothesis space, if you want, or in this case, choosing the space of probability distribution you want to deal with. And once you do this, compute the parameters. That is, imagine the generative process as we've done here, look at your data collection and use Bayes' rule as a way to estimate the parameters. And you can do this in many, many models. I'm giving here another example, which I'm not gonna spend a lot of time on because I wanna get to one more thing. And this is the assumption of hidden Markov models or Markov models in general. I'm gonna get to it next time and give a little bit more details. But basically it's the same kind of thing. You have a probabilistic process of generating a sequence. In this case, it's a sequence over 5 characters. And once you observe sequences, you want to know, okay, so what are the probabilities that govern the generation of this observed sequence? And you think about this process in the following way of being in some state, generating an observation in this state, and then either staying in this state with probability 0.8 or moving to another state and generating a character in that state. I wanna finish with another observation, which is eventually we wanna learn classifiers. So how should we use this general formalism to learn classifiers? We can think about kind of two ways of using this. One is H can be a collection of functions, and given training data, choose the optimal function. Or I don't care about the function, I just care about the prediction. So H is going to be a collection of predictions, and given the data, directly choose what is the optimal prediction. And these two are not necessarily the same, because as our example here shows. So the first formalism suggests to learn a good hypothesis and use it. Once you've chosen the hypothesis, you committed to it, and you're going to make a prediction. So basically this says, choose H by maximizing the a posteriori distribution, argmax over H of P of H given D. And the second one suggests to directly choose a decision. So let's take the following example just to illustrate that these two are not exactly the same. So let's assume that I have a space of 3 hypotheses, H1, H2, H3. And this is, so this I have these 3 hypotheses with the following priors, or the following posterior in this case. P of H1 over the data is 0.4, for H2 it's 0.3, for H3 is also 0.3. So in this case, it's clear that I'm going to choose H1. It's the most probable hypothesis. Now, when I'm getting a new instance, I'm going to make a prediction using my chosen hypothesis. So if H1 of X is 1, H2 of X is 0, and H3 of X is 0, because I chose H1 and committed to it, I'm going to predict 1. However, you can notice that if I did not commit and I'm just looking at what prediction to make, the probability that the value of the function is 1 is only 0.4 from H1, and the probability that it's 0 is 0.6 because both H2 and H3 suggest that it's 0. So these are different decisions, right? So which is the right decision, right? You cannot, in fact, say which is the right decision because you've chosen a process and we are committing to the process. So you can either do this. You can commit to the hypothesis and then make prediction this way. Or you can defer your commitment. Don't commit to the most likely hypothesis until you have to make the decision. And of course, this is going to have computational consequences. Rather than carrying with you a single hypothesis, H1 in this case, which is the most probable hypothesis, given my my previous observations, you're going to carry with you a distribution over hypothesis and make the decision this way. A little bit more formally, what happens here is the following thing. So let's assume that I have a set of possible classification, V, and the elements in V are Vj. So what is the probability of Vj given the data? I'm using the total probability formulas. It's the sum over all hypotheses, P of Vj given Hi and the data, times P of Hi given the data. This is just a total probability formula, or if you want conditional total probability. Now, I can also write it this way because I don't care about the data given that I have the hypothesis already. So P of Vj given Hi and the data is the same as P of Vj given Hi. I don't need the data. Now, let's think about it in the case of the examples that we had before, right? So, in fact, before that, let me just write with the argmax. So what is given this formula, what is the most probable classification I'm going to make? I'm going to take argmax over this, which is argmax over this sum. In the example that I've given before, what is the probability of choosing one given the data? Rather than using H1, I'm going to carry with me the probability distribution over all the H's. So it's going to be the probability of 1 given Hi times the probability of Hi given D, which is 1 times 0.4 plus 0 times 0.3 for H2 plus 0 times 0.3 for H3. So the probability of predicting 1 is just 0.4, and similarly, the probability of predicting 0 is 0.6. So what you've seen here is that if I'm willing to maintain this distribution over Hi, my decision is going to be different, maybe more correct if you want in this time. But really the important thing is that it's an issue of thresholding. When do you want to make the decision? When do you want to commit to something versus making an early decision, committing to one hypothesis that is going to simplify your life later on. And in fact, this is a very important distinction here that all of Bayesian learning has to make decisions on. If you have a layered computation like we have here, first you choose hypothesis, then you use hypothesis to make decisions. When do you make your commitment? Do you make your commitment to a hypothesis and use it? Or do you maintain a probability distribution over hypothesis? And only when you have to make decisions, you make the decision as I suggested here. And this is going to be really the key governing principle that we're going to use next step, which is going to be next week, when we are going to move to discussing Bayes optimal classifiers, and specifically the naive Bayes algorithm. Questions so far? Okay, so what we've done today, just to recap, we talked about the Bayesian paradigm of learning. Everything really boils down to the use of Bayes rule, to deciding what are the H's, to deciding what is the probability distribution that governs the generation of the data. And once you have that, the rest is just instantiation. We've given two instantiation, or three if you want, two very simple in the context of coin, two hypotheses or infinitely many hypotheses, and one a little bit more involved in the case of generating documents. But again, when you go back and look at it, make sure that you understand that what we've done is the same in all cases. We chose the H's, we chose the probability distribution that governs generation of data given the H's, and the rest was just computation. Questions? If not, have a great Thanksgiving break, and I'll see you again next Monday. Bye.